Lecture 4 covers sections 2.4 and 2.6 through 2.7. At the end of today's lecture, you should be able to understand how to use the thermodynamic steam tables in the back of our book. You should also be able to identify the compressed and subcooled saturated liquid regions in our saturated vapor and superheated vapor regions on a TV diagram, as well as in the steam tables. And you should be able to interpolate between two published values within our steam tables. For us to begin, let's talk about a steam table. A steam table has tabulated values of properties, such as specific volume, specific internal energy, specific enthalpy, and specific entropy, based upon temperature and pressure, reflecting our liquid and vapor phases of water. A helpful graph below shows which table we should use if we have a subcooled or compressed liquid, a saturated vapor, or a superheated vapor. We see on our TV diagram to the left that if we have a compressed or subcooled liquid, we are going to use table B.1.4. If we have saturated water, we will use tables B.1.1 or B.1.2. And if we have a superheated vapor, we can use table B.1.3. This is also shown on our PT diagram. If we are existing on our vaporization line, we are going to use tables B.1.1 and B.1.2. If we're existing as a compressed or subcooled liquid, we are going to use table B.1.4. And if we are superheated vapor, we are going to use table B.1.3. Now, our saturated water temperature entry table begins on page 776. Our first column has a temperature entry. This is our temperature of interest. Our second column is our saturation pressure corresponding to that temperature entry. Our third main column is our specific volume, represented in meters cubed per kg. And then we have three columns underneath. The third is that of a saturated liquid, denoted with the subscript F. The fifth column is our saturated vapor, denoted with the subscript G. And our fourth column is the difference between our saturated vapor and saturated liquid specific volume values. The saturated water pressure entry table, B.1.2, starts on page 780. Note that the first column is our pressure entry, and the second column is our corresponding saturation temperature. Now, if we have a substance existing in the saturated state, we should consult both tables. Say we want to determine our saturated vapor specific volume, nu sub g, of water existing at 225 kPa and a temperature of 124.00 degrees centigrade. For us to begin, we could look at table B.1.1 on page 776, and we see we'd have two temperature entries, one of 120 degrees centigrade and one of 125 degrees centigrade. We know our given temperature is 124 degrees centigrade. We could interpolate between this value, which we'll talk about later in this lecture, or if we go to table B.1.2 on page 780, we see we have a 225 kPa pressure entry, and our corresponding saturation temperature is 124 degrees centigrade. So if we go to the fifth column, we can pull out our saturated vapor specific volume, which is taken as 0.79325 meters cubed per kg. If our substance is existing as a compressed or subcooled liquid, we are going to refer to it as a compressed liquid. We notice that our specific volume is going to be strongly dependent upon temperature and very weakly dependent on pressure, such that if we are looking at our specific volume at an elevated pressure and we know the temperature, we can use our saturated water temperature entry table. That is, our specific volume is going to be a function of temperature, and we can take our saturated liquid specific volume evaluated at that temperature. This is because water is an incompressible substance. Regardless of how much we increase our pressure, we are going to see a marginal decrease in our saturated liquid specific volume. That is, we can say our specific volume is not strongly a function of pressure. The compressed liquid water table, B.1.4, starts on page 790. Notice how we have our subpressure entries. That is, we have a 500 kPa pressure entry, and the number within parentheses, 151.86 degrees centigrade, corresponds to our saturation temperature, i.e. the first entry of our temperature column. And we know we're given specific volume, specific internal energy, specific enthalpy, and specific entropy, nu, u, h, and s, on the top. We don't have a saturated vapor or saturated liquid state. These values are undefined when we are in this region. Now we know we have a 2000 kPa pressure entry, and we have corresponding specific volume, specific internal energy, specific enthalpy, and specific entropy values as a function of temperature. Say we wanted to determine the specific volume of water existing at 10,000 kPa at a temperature of 60 degrees centigrade, and we want to use our compressed liquid water table in B.1.4. we will go to our 10,000 kPa pressure subentry and look for a temperature of 60 degrees centigrade. And we find our specific volume is 0.001013 meters cubed per kg. Now, how does this compare if we take our saturated liquid specific volume, evaluate it at 60 degrees centigrade from our temperature entry table, B.1.1? We find that our saturated liquid specific volume, taken from table B.1.1 at a temperature of 60 degrees centigrade, is 0.001017 meters cubed per kg. Or the percent difference between these two is 0.39%. That is to say, we can use our saturated water temperature entry table if we know the temperature of a liquid state at an elevated pressure, in lieu of our compressed liquid water table. Now, a superheated vapor state is when our temperature is greater than our saturation temperature for a given saturation pressure, or conversely, when our pressure is less than our saturation pressure for a given saturation temperature. And our superheated vapor water table, B.1.3, starts on page 784. And this follows the same format as our compressed liquid water table, where we have pressure subentries as a function of temperature, and we only have our specific volume, specific internal energy, specific enthalpy, and specific entropy published. There is no sub F or sub G entry. Suppose we are looking for a specific volume of water at 400 degrees centigrade and a pressure of 22,089 kPa. Is this possible? If we go to table B.1.1 and go down our temperature entries all the way to 374.1 degrees centigrade, on page 778, we see we reached our critical temperature with a corresponding critical pressure of 22,089 kPa. We may say that we are in a supercritical fluid region. However, if we turn to our superheated vapor tables, table B.1.3 on page 789, we see we do have a pressure entry of 20,000 kPa with a corresponding temperature of 400 degrees centigrade, as well as a pressure entry of 30,000 kPa and a corresponding temperature entry of 400 degrees centigrade. That is, we do have these published values on our superheated vapor water tables, and thus we can pull the value. To summarize, we can relate our temperature or saturation temperature or pressure to saturation pressure such that we can refer to which table we need to use. If T is equal to Tsat and P is equal to Psat, we are existing as a saturated water, and we will use tables B.1.1 and B.1.2. If our temperature is less than our saturation and our pressure is equal to our saturation, we are going to exist as a subcooled liquid, and we can use table B.1.4 and B.1.1. If our temperature is equal to our saturation and our pressure is greater than our saturation, we have a compressed liquid, and we can use table B.1.4 and B.1.1. Lastly, if our temperature is greater than saturation and our pressure is equal to our saturation, we are a superheated vapor. Or if our temperature is equal to our saturation and our pressure is less than our saturation, we are also existing as a superheated vapor, and we will use table B.1.3. If the value is not on the table, you are doing something fundamentally incorrect. These tables are the backbone of all thermodynamic cycles: the Rankine cycle, the Otto cycle, the Diesel cycle. If they were wrong, modern civilization would not exist. We would not have had steam engines during the Industrial Revolution, nor would we have steam power plants now providing us electricity.